Today, we're diving into a really mind-blowing technique coming out of MIT. It's about a world where artificial intelligence isn't just crunching numbers, it's actually becoming an architect for our physical world, inventing brand new materials completely from scratch.
Just think about that for a second. What if you needed a material that was, say, stronger than steel, but light as a feather? Or maybe one that conducts electricity with zero loss at room temperature? Instead of hoping to find it somewhere, what if you could just invent it? That's the huge question that's driving this entire revolution we're talking about today.
Now, to really get why this is such a big deal, we gotta look at how things used to be done. For, well, basically all of history, finding new materials has been like searching for a specific needle in a haystack the size of the universe. The traditional way is a slow, really painstaking process. Scientists would come up with an idea, a hypothesis, then spend months, sometimes years, in a lab trying to make the thing. And then, after all that, they'd test it, just hoping it had the properties they were looking for. It was all trial and error. This quote here, it just nails the problem. That phrase, the vastness of chemical space, it's a poetic way of saying there are more possible ways to combine atoms than we could ever test. Not in a million lifetimes. We've basically been exploring a tiny, tiny corner of this massive, undiscovered universe of materials. And the result of all that inefficiency, it's pretty stark. Getting just one new material from an idea in a lab to a product you can actually use could take decades. Decades. That's a massive bottleneck that has slowed down innovation in everything from medicine to energy. But as you can see, that's starting to change, and fast. We're talking about shrinking that timeline from decades down to months.
So, how did the researchers at MIT do it? How did they break this cycle? Well, they didn't just speed up the old process. They flipped the whole thing completely on its head. Instead of searching for that needle in the haystack, they're teaching an AI how to build the exact needle they need right from the start. So this is the key difference right here, moving from forward screening to what's called inverse design. The old way, on the left, that's our guess and check method. You make something, test it, and hope for the best. But inverse design, on the right, that's a total game changer. You start at the end. You tell the AI, hey, I need a material with these exact properties, and the AI actually works backward to design the atomic structure that will give you what you want. And this is where it gets really elegant. It's not just a one-and-done thing. It's a closed loop. First, the AI comes up with some possible designs. Then, and this is the cool part, an autonomous robotic lab, the A-Lab, actually makes and tests tiny samples of them. The results from those real-world tests get fed right back into the AI. The AI learns from what worked and what didn't, and its next batch of suggestions gets even better. It literally gets smarter with every single cycle. Okay, so this all sounds amazing in theory, right? But does it actually work? Can a bunch of code really invent a physical material that you can, hold in your hand? Well, the answer is a huge, resounding yes. And here is the proof. Look at this. These aren't just simulations on a screen. These are two completely new materials, dreamed up by the AI and then built by that robotic lab. Now, just for some quick context, paramagnetic means a material is weakly attracted to a magnet, and diamagnetic means it's weakly repelled. Discovering new materials with really specific magnetic properties like these is absolutely critical for things like next-gen sensors and data storage. And the main point is, these materials simply did not exist before the AI designed them. To really understand how powerful this is, let's just look at the raw numbers. The first one is 95%. So what does that mean? Well, when the AI generated almost 26,000 potential designs for materials, the computer models could successfully simulate them almost every single time. That shows the AI isn't just spitting out random nonsense, it's fluently speaking the language of physics and chemistry. But this next number, this one is even more incredible. 53%. That's the percentage of the AI's designs that were actually structurally stable. This is mind-blowing. It proves the AI isn't just throwing digital atoms together and hoping they stick. Over half of its unique creations could actually exist in the real world. It's designing for reality, not just for theory. Okay, so we've got a powerful new technique, and we know it works. But what does this all mean for you and me? Let's take a look at the real-world revolution that's already kicking off because of this. Yeah, this is not science fiction. Industries are already all over this. The aerospace and defense sector, for example, is a huge early adopter. They're making up almost a third of the market, using AI to design materials for planes and spacecraft that are lighter, stronger, and way more resilient. But the impact on our health could be even more profound. You have to remember, drug discovery is basically a form of materials design, and AI is just crushing the old timelines. There's a company in silico medicine that used AI to develop a new treatment and got it to human trials in less than 18 months. Normally, that process takes 5 to 10 years. This is going to save lives, period. And you're seeing this pop up everywhere. General Motors is designing lighter car parts to make them more fuel efficient. In the energy sector, AI is figuring out the absolute best places to put wind turbines. It's even being used for predictive maintenance on our power grid to help prevent blackouts. It's touching almost every major industry you can think of. So, where does all this go from here? We are, no exaggeration, at the very beginning of a new era of creation. But there are still some pretty big hurdles we need to think about.
It's not a perfectly smooth road ahead. The computations can still be really slow, creating bottlenecks in that feedback loop we talked about. There's also a cultural thing, getting an entire scientific community to move away from old static databases and embrace these new dynamic AI models. That takes time. And maybe most importantly, as this tech gets faster and faster, we need to have a serious conversation about the rules and ethical frameworks to guide it. But make no mistake, the change is here, and it's real. We're seeing a fundamental paradigm shift right before our eyes. We're leaving behind a world of slow, accidental discovery and entering an age of intentional, predictive, and AI-guided creation. So, I'll leave you with this one final thought. For pretty much all of human history, we've been limited by the materials we could find or stumble upon. We're now building a future where our only real limit is our imagination. And as AI steps into the role of architect, the defining question for all of us is going to be, how will we choose to guide its hand?